Hello, good afternoon to all of you. So today we are going to start our third counseling session, which is all about the course BMTC-131 calculation. And today our main focus point of discussion is all about differentiation. Hello, have you any question? Hello, hello, can you hear me? Hello, do you have any question? So let us start our discussion. It is all about the differentiation. So in this differentiation, we have three units, and in these three units, first we have to discuss about the definition of derivative, then some basic theorems and properties of differentiation, and finally we are discussing higher order derivatives, and then these higher order derivatives we will discuss with some examples and exercise. And finally, this idea will be adopted to discuss about the parametric representation of curves and partial fractions. So now, let us begin with the discussion of the definition of derivative. Now, for that one, hello. So I am directly going to the summary of this particular differentiation chapter. In that summary, we are going to discuss all the important points. And as you can see here in the summary chapter, first is the definition of derivative, and here the definition goes like that. Here we have a function in the form of y equal to f of x, and the derivative is given in the form of its definition, that is f s equals to limit delta x tends to 0, and the numerator is f of x plus delta x minus f of x all divided by delta x. So this particular quotient or difference of quotient is known as the derivative of the function at the point x. So clearly, if we are observing, if we are focusing in the numerator, there is a difference between the value of the function at x and the value of the function at x plus delta x. So here it will be now denoted by f dash x. Now the function will be represented by f prime or f dash, and the geometrical meaning of f dash x is the slope of the curve at the point x, and it can be represented like that. F dash x at x0 is also known as the slope of the function at the point x0, and can be represented by tan theta, because in two-dimensional geometry we know that tan theta is also the slope of a straight line or a curve at a certain point x. So this is the basic representation of the first differentiation at the point x. Now let us look at the second point, and here in the second point, the difference quotient, that is f of x plus delta x minus f of x divided by delta x. This is known as difference quotient, and under limiting condition, when delta x is very small, it is approaches to 0, it will be, it gives us the value of the derivative at x equal to 0 or at any point x. So these are the basic conditions under which we can define the derivative of a point at x equal at x at any point x. So now the necessary condition is that whenever a function is continuous, then derivative may exist. Here we can say that, but the converse is true. That means a differentiable function is always continuous at the point x. So let us see the PDF which was presented here, and according to the PDF we can use now this definition to find out the derivative of a constant function, and here the function is in the form of f of x equals to c, and the derivative of constant function is equals to 0, because we know that constant function does not changes its value at any point. So that's why in the numerator of the definition the change will be 0. So that's why 0 by any value will be final gives us 0 value. So that's why derivative of a constant function will always be 0. Now let us look at the next point. Here there is a small formula which is all about the derivative of monomials, and here the degree of the monomial is x to the power n. And by using the same definition which was discussed earlier in the beginning of this session, we can apply, and we can also easily calculate or estimate the formula and the result, and it will be n into x to the power n minus 1. And here the result will be exist when x is not equals to 0, and the condition is satisfied when n is less than 0, that means negative numbers. That means this particular formula is applicable for all the monomials of degree positive or negative, but it must be an integer or fraction, but x should not be 0 here, because if x will be 0 then the function will be 0, and we are not able to calculate the value of the derivative of the function at the point. So now let us look at the sixth point of this particular chapter, and here there is a small function given in the form of square root, and the function is y equal to root over of x. And again we are using the same basic definition of the derivative, or the definition is also known as ab initio ratio, or first principle for the derivative of the function at any point x. And again by using the same definition of difference quotient, we can calculate easily the value will be 2 into root x, and this value it exists when x is greater than 0, because as we know root over is defined for positive real numbers. So that's why the result will exist only for all the values of x when x is greater than 0. So in this way we can very easily use the definition of the derivative, also known as first principle or ab initio ratio, by using or in the environment of limit. And basically we are using in the limiting process, we are using small delta x, the small increment in the direction of x-axis, to represent in the form of f dash x. Now let us moving towards the next point, that is the differentiation or derivative of absolute value function, that is mod x. And here the function is mod x. So now we are trying to find out the derivative of the function mod x at x equals to 0. But whenever we're going to calculate the derivative of the function at x equals to 0, here the limit does not exist, because the limit will exist when the right hand limit and left hand limit both exist and equal. Then limit exists, and you can say that that is the limit of the function at a certain point. So here in this particular function, modulus function y equal to mod x, is we have two different values. Mod x gives us x when x is itself positive or 0. Mod x gives us negative minus x when x is itself negative number. So here we can easily say that the right hand limit or right hand derivative when we are approaching x from the right hand side, and the left hand limit when we are approaching to the point x from the left hand side. Here the right hand limit and left hand limit both exist, but right hand limit is equals to 1 and left hand limit will be minus 1. So that's why the value are not equal. So conclusion will be that the function does not have the derivative or differentiable at the point x equals to 0. Now you may follow the definition for the simple calculation for right hand limit and limit. Now let us begin to the next point of this particular unit, and that is all about the differentiation. And here the first point is when a parameter or a constant c is multiplied with a function, then how we can use the derivative process for this kind of function when a scalar is multiplied with a function. So here c is a constant, so that can be taken out of our calculation, and we can represent c into derivative of f with respect to x. So same process will be adopted in the following addition, subtraction and multiplication process. So look at the second point. So these are the basic fundamental properties for the differentiation of two functions under summation, subtraction, multiplication and division. So here in the second point of summation rule, this particular formula is also known as summation rule, and here two functions f and z both are differentiable function and represent under the binary operation summation, and we are going to calculate the derivative of sum of these two functions f and z, and the right hand side the result will be derivative of f with respect to x plus derivative of z with respect to x. So that means derivative of sum of two functions will be exactly same as the sum of derivative of two functions. The language will be very easily represented one. Now let us come forward to the third point, and here we are going to discuss about the derivative of difference. And in this derivative of difference, we have again same two kind of functions. First function is f, second function is z, and we represent that one by using the difference of both the functions f minus zx. For your reference, you may look at your screen. In the screen, it was already presented or visualized in the form of point 8. In point 8, we are discussing in this particular third formula, and that is all about the derivative of difference of two functions. So as you can see here, derivative of first function with respect to x minus derivative of second function with respect to x. And in language, we can also represent in a simple sentence, and it will be like that. derivative of difference of two functions is equals to difference of their derivatives. Now, let us moving towards the fourth point, and here this particular formula is known as product rule of derivative. That means we are multiplying two functions f and z together. After multiplication, we are able to, or we are going to calculate the derivative of two functions in the with respect to x. So here we have to note the point is that both the function must be defined and continuous at the same point x, and the right hand side, the result will be first function free. Look at carefully. The first function is free multiplied with the derivative of second function plus second function g is free multiplied with the derivative of first function. So now that will be known as the product rule of derivative, and in language you can say that derivative of product of two functions is equals to summation of the product of first function and derivative of second function and derivative of first function into second function. So in language you can represent in the same form. And these are the simple and basic formula which are useful to find out some problems of exercise. But condition is that all the function must be continuous at these points. Now let us discuss about the next point, and that is that derivative of quotient of two functions. So here f and z both are continuous function for each and every point of x in its domain. Then we can define the derivative of quotient of two functions, that is a fraction fx divided by gx. Then look at the right hand side of the region. Here in the denominator to the right hand side, there is the square of z, but in the numerator, there is the difference of two quantity, and here the first term is function denominator is free, but multiplied with the derivative of the numerator minus the numerator is free and multiplied with the derivative of the denominator. But condition is that the denominator should not be 0 for any value of x in its domain. So this is the formula for the quotient rule of derivative. And again, I'm going to repeat the same formula which was represented in the form of quotient. And here in the denominator, we are using the square of the denominator, that is z, and the numerator, that is difference of two quantities. The first term is the product of the denominator and derivative of numerator minus the second term will be numerator into multiplied by the derivative of the denominator. And here we have to must visualize the condition that focus the condition that the function g should not be here 0. Similarly, we can also calculate the derivative of reciprocal of a function. So here we are representing in the sixth property derivative of reciprocal of a function, that is d by dx of 1 by f is equals to the same formula. The quotient rule will be applicable here to discuss the derivative of reciprocal of the function 1 by f of x. And here the result will be in the denominator as a square of the denominator, that is square of the function f, and in the numerator it is minus of f dash x, that means minus of first derivative of x. And again you have to focus in the condition that the function should not be 0 for any value of x in its domain. So these are the basic fundamental rules in differentiation. Then we may also use the chain rule. So here in chain rule, generally this chain rule is applicable to find out the derivative of a function when a function is a composite function, or two or more than two functions are composed together to form a new function. This kind of functions was discussed in our first counseling session, and these functions are known as composite functions. And whenever we have a composite function, to find out the derivative of this kind of composite function, we are using this chain rule. So here, very carefully, we can see that y is a function of x, u is also a function of x, and then if we are going to calculate the derivative of y with respect to x, we represent here derivative of y with respect to u multiplied with derivative of u with respect to x. So these are the simple product formula we are applying to find out the derivative of complex functions. So now let us talk about the derivative of trigonometric functions. As we know, we have exactly 6 trigonometric functions, and these are sin x, cos x, tan x, cot x, sec x, and cosec x. And now the formula or the definition or the first principle or the ab initio ratio that we discussed in the beginning of this session will be applicable to find out the derivative of trigonometric functions. So again, by using the same definition, we have the derivative of sin x equals to cos x and derivative of cos x equals to minus sin x. Similarly, all the derivatives of the other trigonometric functions can be calculated very easily. And the same process will also be adopted to find out the derivative of inverse trigonometric functions as well. And now we can see, you may visualize. So here in this table, it was listed all the derivatives of inverse trigonometric functions. So as you can see, the first function is sin inverse x. And again, if we are using the same process of calculation or the definition of derivative, then the result will be 1 by root over of 1 minus x square. And similarly, the same process will be adopted to calculate the derivative of cos inverse x, and that will give us the result minus 1 divided by root over of 1 minus x square. So in this way, we can use all these inverse trigonometric functions to find out the result of their derivatives. So in differentiation, or in the first unit of differentiation, all the basic definitions and all the basic formula and properties and algebra of differentiations are given, and we are discussing one by one. Now let us moving towards the next unit, that is all about some more derivatives. So here in some more derivatives, we are focusing on the differentiation of exponential function, differentiation of logarithms, differentiation of some hyperbolic functions, and differentiation of some inverse hyperbolic functions. So now let us moving towards the summary of the second module, and that is in the page number 81. So if you have the course material, the book, you may also follow the page number 81, and that is the summary of the second unit, and that is about all about the derivative of some more functions. So here, as you can see in the table, we have listed some standard functions. So first function is an exponential function that is represented in the form of e to the power x. And as we know, exponential function can be represented in the form of a to the power x, and a be any real number. But generally, exponential functions always indicate about e to the power x, and as we know, e, small e, is an irrational number whose values lies between 2 and 3. So again, we adopt the same process of calculation to find out the derivative of exponential function e to the power x, and surprisingly, we found that the value or the result or the output of the derivative of exponential function will be exactly the same as e to the power x. Now look at the next function. Next function is here ln x or ln x. So here Again, we are using the same process of calculation, or we are using the definition of the derivative or first principle, or we can say that f initial ratio. We can find the result will be 1 by x. Similarly, we can add up the definition to prove the result or the derivatives. So generally, the proof of these functions are not necessary, but we have to memorize all these results as a formula that are useful to solve problems of exercise or examples. Now, similarly, in the second point, second table represents the derivative of inverse trigonometric functions. And here in the second table, as you can see, the functions are listed in the form of sine hyperbolic inverse. So here the functions are sine hyperbolic inverse x, and the derivative of sine hyperbolic x is equals to 1 by root over of x square plus 1. Similarly, inverse hyperbolic function is cos hyperbolic inverse x, and its derivative is 1 by under root x square minus 1. So the same process of calculation of definition will be adopted to prove all these results. But again, I am repeating, we are not going to prove all the results, but we have to memorize this formula for future use. Now, logarithmic differentiation. So here in logarithmic differentiation, that is in the fourth point, logarithmic differentiation. So to find out the logarithmic differentiation, we have to take modulus. If the function attains a negative value for some x, then we have to take logarithm in both sides. After taking logarithm in both sides, we have to apply the same process of calculation. That means we can apply the formula of derivatives to find out the result if the functions are given in the form of power of a power or in the form of exponential function. And similarly, have you any question? Tilochan Sahu, can you hear me?
Yeah, no sir.
ନମସ୍କାର
Hello.
କିଛି ପଚାରିବାର ଅଛି?
ନାଇଁ ଆଜ୍ଞା।
ଆଚ୍ଛା କି ବହି ବହି କିଛି ପାଖରେ ଅଛି?
ନାଇଁ ମୁଇଁ ଏବେ ଜାଣିନି ଘରରେ ବହି ଅଛି।
ଆଚ୍ଛା ଆଚ୍ଛା ଆମର ତ ଡିଟେଲ ପ୍ରୋଗ୍ରାମ ଚାର୍ଟ ମିଳିଯାଇଛି ତ?
ହଁ ଆଜ୍ଞା।
ହଉ ଠିକ ଅଛି, ସେଇ ଅନୁସାରେ ଆମେ ସେସନ ଷ୍ଟୁଡେଣ୍ଟ ପାସ୍ କରି ଛୋଟ ରହିବ।
ହଁ।
ଆଚ୍ଛା ଆମେ ଆଜି ଡିସ୍କସ୍ କରୁଛୁ थर्ड सेशन में अच्छे डिफरेंशिएशन माने हम डेरिवेटिव देखो कि हमें इंटरमीडिएट सेशन में प्लस टू लेवल रे पढ़िथिबो तो सही गुडा काम में रिवाइज करछु
आया
जदि किछि डाउट थिबो
आया
तो पचार परिबो
ठीक हो जाए।
हां तो ठीक अछि तबे माइक टा को म्यूट कर दियो।
हां
Oh. So now we are going to discuss the derivative of implicit functions. So, an implicit function तिलोचन साहू
आया
हाँ तुम से माइक टा को म्यूट कर दियो।
हां
हाँ कहीं ना बाकी साउंड गुडा क्लियर आसु नहीं। So thank you Tilochon Sahu. So now we are at the fourth point, and here in the fourth point that is the logarithmic differentiation. And as you can see, in logarithmic differentiation, the process is very simple, and that can be carried out in three different steps. In first step, the function, if the function will attain any negative value, then we have to take modulus in both sides. Then after taking modulus, both the quantities will be turned positive. Then after making all the term positive, then we are able to take logarithm in both sides. Then after taking logarithm, the third step will be the derivative using the chain rule. And simply we are using the derivative of log f of x, and the result will be first derivative f dash x divided by fx. And similarly, we can add up the differentiation process to find out the derivative of the parametric equations. And parametric equations, as we know, it is x equal to f of t, the function f in the form of t that was represented in the form of x, and y. So we are discussing the sixth point, and here x is a function of t and y is a function of t, and the function of t in x is represented by f, and the function of t in y is represented by g. So now, whenever this kind of representations are given, this kind of representations or notations of the form is known as the parametric equation or parametric form of the expression. So here, the derivative dy by dx will be dy by dt divided by dx by dt. Very simply, you can say that first we are going to calculate the derivative of y with respect to t, then we are going to calculate the derivative of x with respect to t, and finally we are dividing, and the result will gives us the derivative of the function y with respect to x, that is dy by dx. So these are the simple basic formula, the process we are adopting to solve problems of your exercise under this chapter of differentiation. So many different chapters, so many different examples, so many different problems are given in your textbook in a very simple manner. Please go through all the different examples with the help of the formula and the rule which I discuss now. And now let us moving towards the next unit, that is all about the higher order derivatives. So higher order derivatives present in the page number 91. So now I request, if all of you have your book, then please move to the page number 81. So in 81, in page number 91, and 91 is dedicated to the higher order derivatives. That means till now, whatever we discuss, all the basic rules and formula and the conditions are defined over the first derivative only. But if we are going to calculate the derivative of a function more than one times, these are known as higher order derivatives. So whenever we have to calculate the higher order derivative, that means here the order must be greater than 1. So let us begin with the second order derivative. So now, to discuss about the basic idea about the higher order derivative, let us move towards the summary of this particular chapter. And the summary of this chapter will be in the page number 120. And in 120, we have all other basic introductions of higher order derivative and some applications of higher order derivatives like Leibniz theorem and the linear approximation using the first order and higher order derivative, and then the quadratic approximation of a function with higher order derivative. And the same idea will be now extended to other two theorems like Maclaurin polynomial and Taylor's polynomial in the form of higher order derivative. So let us begin our discussion of higher order derivative with the first simple example. And here let us propose an example. Now look at this example number 4. Now in example number 4, the equation or the function is given in parametric form. So here x equals to a into cos t plus t sin t, and y equal to given.
Good evening, sir. Excuse me, can I get to know something?
Yes, why not, please?
Sir, actually, I got this mail today only, and yes, means it was continuing from 2 days before, I think so. So
Yeah, we have
means
started. We have
it.
started from 8.
Oh, and other subjects are also going on, sir. I just want to ask.
So if you have got the mail, in that mail there is a clear description all about your programs and schedules.
Yes, sir, but only three subjects are there in that scheduled, and other two subjects are not mine. I am a student of BSc. So that's why I
Okay.
was just asking and confirming that.
So then it is better if you are contact with our Signu Center of this college, Government College Sundargarh. They will better
Oh,
clarify your doubts. Okay.
okay. Thank you, sir.
Is there any question related to this topic of differentiation?
Sir, actually, I just joined. Means I just joined it now only. So I was just preparing that same thing. I was not done that
Okay,
properly. So
okay.
sorry.
So we are discussing about the differentiation, and the differentiations are already these are well known to us in 10 plus 2 level, and all the basic
Oh,
things we are discussing till now.
oh, thank you. And sir,
Yeah,
sets and relation function has completed already.
that was completed in the first session.
Sir, but I was told very lately, and I haven't followed up with the class. So how can I catch up with all these things now?
So the class has been recorded. You may follow the class, but to clear your doubts, you have to contact separately.
Okay.
Whether
How?
it may be in mail or through our WhatsApp.
Okay. Sir, but
Okay.
WhatsApp number, I don't have anything like that. Is it given in that mail also?
Okay. The program chart given to you. In the program
Hmm.
chart, all the details has been given. Our contact number, mail ID
Okay,
may be
okay.
given, but our contact number is given. If you have any
Hmm.
query, then you may please give us in WhatsApp.
Okay, thank you, sir.
Okay.
Sir,
Thank
sorry,
you.
sir. Sorry for disturbance.
Oh,
I
no
really
problem. No problem. We are here to serve you. Okay. Thank you.
uh,
So we are in the point or discussion about example number 4, that is all about the derivative or higher order derivative, and here in this particular example, so you can zoom it also in your mobile phone, you may also zoom it to look at this example number 4, and this example number 4 is given in parametric form, because here the function x is given in the form of t and y is also given in the form of t. And to calculate this kind of expression or the form, parametric form, we are using the same process of calculation. That means first we differentiate the first function x with respect to t, and then we have to differentiate the second function y with respect to t. And finally, we are dividing to get our result. That means the first order derivative of y with respect to x will be now represented by dy by dt divided by dx by dt. So here the result will be tan t. In the same way, if we repeat the same process of calculation, but here when you are going to calculate the higher order derivative of first order, then we have to use the chain rule. So look at the chain rule. So you may zoom out the rule. So that was written here, and this one, the d square y of dx square equals to, it can also be written as dy dx of derivative of y with respect to x. So very clearly we can see here the differential operator dy dx is used twice. Dy dx again dy dx of y. So that's why this is known as the second order derivative of y with respect to x. Now, as we are going to calculate the second order derivative of y with respect to x, but here clearly or very interestingly we can see that the functions which was given to us is in the form of t, but we are going to calculate the derivative with respect to x. So that's why we have to use here the chain rule, and first we have to calculate the derivative of the result that was obtained in dy by dx, that is tan t, with respect to t. Then finally we have to calculate the derivative with respect to x, that means dt by dx. So that was the simple trick we have to use whenever we are adopting this kind of parametric representation in higher order derivative. And here the result will be obtained after calculating the derivative of tan t, that is x square t according to the formula. Again we are using the derivative of t with respect to x. That means here the derivative of t with respect to x can be written from the value of dx by dt. So both are multiplied together and finally you can get the result in the form of 1 divided by a into t into cos qt. So that is the final result of this example number 4. So all the examples are given in very lucid manner, and all are advised to go through each and every examples to clear about the basic formula which we'll discuss in this session. And now let us moving towards higher order derivatives like third order, fourth order, or nth order differentiation. These are also known as the successive differentiation. Higher order derivatives are also known as successive differentiation of a function. So here the first point is nth derivative of exponential function e to the power x with respect to x, and the derivative of exponential function x with respect to x. So let us move to the point is number 99. Is number 99. This one. So nth derivative of exponential function, that is e to the power ax with respect to x. So we can represent y equal to e to the power x, and the first derivative will gives us a into e to the power ax, and the second derivative will gives us a into a, that is a square into e to the power ax. So look at the pattern we have represented in the left hand side. All the derivatives are represent in the power of the function y inside the parenthesis, because this is the standard notation we are following to represent the higher order derivative of a function. So keep in mind that whenever we are using the higher order derivative of a function, we are using parenthesis in the power. Now the result has been written in the right hand side. The third order result will be written in the right hand side, that is aq into e to the power ax. And similarly, if we are repeating the process again and again up to n times, the result will be a to the power n into e to the power ax, a to the power n into e to the power x. And finally, that will be the nth derivative of the exponential function. So the process will be same for every function, whether it may be exponential function or it may be logarithmic function. The process will same. That means we are calculating one by one derivative up to the nth order derivative. So let us now focusing on the next example or the standard function, that is all about the polynomial function of degree n. And here we represent y as a function of ax plus m all to the power m. So here m may be integer, any real number. So here all other derivatives are represented in the form of y1, y2 and y3, and we are using here the basic formula of x to the power n formula, that is the formula of monomial that was discussed in the beginning of this session, derivative of this kind of function. So here the result will be m into a into ax plus b whole to the power m minus 1. And the calculations are very simple and easy. We have to follow systematically along with the particular formula of that function. So finally, look at the nth order derivative. If we are repeating the same process of calculation, the nth order derivative will be like that: m into m minus 1, m minus 2 in the third order derivative, and then in nth order we have a to the power n all into x plus b whole to the power n minus 1. So this kind of pattern we will find if we are going to calculate the nth derivative of the polynomial function, and that is in the form of x plus b whole to the power m with respect to x. So this is the main focus point of discussion in this particular chapter. Now let us moving towards the summary of this chapter, and in the summary some other points will be discussed one by one. So the summary of this chapter is given in page number 120. Let us go to the page number 120. So here the chapter summary. So in this summary, in first point that was we have discussed, that is the higher order derivative of function or successive derivative of a function. But look at the second point in the page number 120. The second point is the formula or derived formula of Leibniz theorem. And this Leibniz theorem is applicable to find out the nth order derivative of a product of two functions. So again I repeat the sentence. So this Leibniz theorem is applicable. If you may also zoom out to see this particular theorem, we are going to now discuss that one. So that is Leibniz theorem. So here, this Leibniz theorem help us to find out the nth order derivative of the product of two functions. So whenever we have product of two functions and we have to calculate nth order derivative, we have to follow this process of calculation. So very simple representation is given. So look at that: u into v, that is u is a function of x, v is a function of x, suppose, and both are multiplied together, that is the product of the function u and v, and in the power it is given n inside parenthesis or bracket. That means you have to calculate the nth order derivative of product of two function u and v, and the result is given in the right hand side. Look at the right hand side. The first one is Cn0. So Cn0 means this is the combination formula, and as we know, Cn0 is combination of n thing taking 0 at a time. So we have to use here the formula of combination, and that is n factorial divided by 0 factorial into n plus 0 factorial. And in the second term here, look at carefully, focus in the second term, and in the second term we are representing capital C n comma 1. That means now 0 8 is equals to 1, and look at the power of u. Power of u means here the derivative of u will be n minus 1, just one less before the previous term, into v1. v1 means the first derivative of the second function v. Similarly, you can see that in combination the value will be integers 0, 1, 2, 3 like that, and the order of derivative of u is gradually decreasing, whereas the order of the derivative of the second function is gradually increasing up to n. So here If we focus in the last term, it is clearly, you can observe that the last term is the combination of anything n at a time, and here u means the zeroth order derivative. That means no derivative means the function will be remaining unchanged in the same form of u. And vn inside bracket means we have to find out or calculate the nth order derivative of the function. So these are the formula we have to memorize to find out the nth order derivative of product of two functions. Now three. Now three. Third point is the point dedicated to the linear approximation of a function f about any point x0. So here the function, that means here we are going to approximate the function in the form of a straight line, and the expression is quite simple. In the right hand side we are expressing the way f of x0 plus f dash x0 into x minus x0. Now look at the expression and please focus in the sign, and that is asymptotic equal. That means approximately equal. The function is approximately equals to the right hand side of the expression. So that's why it is known as, we are using here the word approximation. So the function f is approximately equals to the right hand side, and clearly the right hand side is a linear expression represent a straight line. So that's why it is known as linear approximation of a function about a point x0. And now the idea can be extended to form a quadratic approximation of a function f about the point x0. So here the expression of the right hand side in point number 3 is extended to the second order form. That means here the first term f of x0, second term is f dash x0 x minus x0, and third term is double derivative of the function at the point x0 divided by 2 factorial into x minus x0. You may also zoom out that particular formula represent in fourth point. This is the fourth point we're discussing now. And here f of x0 plus f dash x0 x minus x0 plus double derivative of x0 divided by 2 factorial and into x minus x0 squared. So this is the expression of the formula we are adopting, we are using to find out the quadratic approximation of a function when a function is differentiable at a certain point x0. And similarly, if we are going to extend the same process of calculation, the same expression will be developed as a series, and this series is known as a Taylor's polynomial or Taylor series. Look at the expression in represent in point number 6. So point number 6 is totally dedicated to the Taylor's theorem or Taylor's polynomial of a function f about the point x. But condition is that the function must be n times differentiable at the same point x0 at which we are going to express in the form of a series. So let us focus in the formula. The formula is same. The first, second, third term are exactly same as to the formula of 3 and 4 that we discussed in linear approximation and quadratic approximation. So clearly you can see the function is approximately equals to, in the right hand side we have a summation of n terms, and here the first term begins with the functional value at x0, second term is x minus x0 into first derivative at x0. Similarly the third term is square of x minus x0 into f double derivative of x with respect to 2 factorial, and here the last nth term will represent x minus x0 whole to the power n into nth derivative of the function f with respect to x0 divided by n factorial. So these are the standard Taylor's polynomial for a function at a point which is the function is differentiable at the point x0. And in the same Taylor's formula, if we putting or using the value of x0 equals to 0, we have the formula number 5 that was represented in point 5. So if we are going to compare the formula represent in point 5 and represent in point 6, both are exactly same, but only difference is that in the Maclaurin's polynomial we are using the point at origin. So 0 means origin. So here x0 point is all are 0. But in the Taylor's polynomial, that is different from origin or other than origin. So this is the only difference between the formula in Maclaurin's polynomial and the formula in Taylor's polynomial. In Taylor's polynomial, we are using a certain fixed point, that is x0. If the certain point x0 will be fixed at origin, then the same formula will gives us a polynomial that is known as Maclaurin's polynomial of a function at a certain point x. And in this example and the questions given in your exercise are given to find out the linear approximation or quadratic approximation, or that is all about to find out the Taylor series or Taylor's polynomial of a function at a point x0. And also the Taylor's polynomial will be developed in the form of the Maclaurin's polynomial whenever we're going to substitute the value of x0 will be 0. So these are all about the higher order derivatives, and we have discussed that is the block number 3, that is all about differentiation. So I'm going for a quick review what we were discussing in this session. We have discussed in the first unit, that is all about the basic about the differentiation, that means definition. Definition is known as first principle or ab initio ratio, and the definitions was used to find out the derivative of certain elementary functions like identity functions, constant functions, trigonometric functions, inverse trigonometric functions, exponential functions, logarithmic functions. All are used to find out the derivative with the help of this. Then we are using the
Hello.
same.
Hello, sir. Good evening.
Good evening.
Sir, Sunil
Good
Vishwajit.
morning. Hello, Vishwajit. Any question?
Sir, can I ask in Odia?
ପଚାରି ପାର।
Sir, you differentiation ro kete mark padibo mane BSc te jenti?
डिफरेंशिएशन में केते मार्क पड़ो सेटा तुमर जो सिलेबस दिया हेथिबो कोर्स मटेरियल संगे सेथरे डिटेल्स लिखा हेथिबो को ब्लॉक रो केते मार्क आसीबो तुमर जो प्रोग्राम अछि BMTC 131 कैलकुलस अछि सेते को पर्टिकुलर ब्लॉक रो बा को पर्टिकुलर ब्लॉक रो केते केते मार्क पूरा डिवाइड है सेटा क्लियरली मेंशन है कि थिबो जो पर्टिकुलर चार्ट मोपटे वर्तमान नाही।
हाउ सर?
अगर तुम्हें चाहिए साइट को जाए कि इग्नो साइट को जाए कि डिटेल डाउनलोड करके निजे देख पारिबो। ठीक अछि
सर, ठीक। ओके सर।
आगु जी क्वेश्चन?
नो सर।
अच्छा वही रखि तो पाखरे कि बुझी होछि?
हां, डिफरेंशिएशन और सॉरी सलानी
हाउ ठीक अछि।
इंटीग्रेशन चलती।
हाउ
हाउ सर।
हाउ थैंक यू। So today this much from this session, and we are covering the differentiation part, and in this differentiation we are covering the basic idea about differentiation and derivatives from some different kind of functions, and we are discussing about the higher order derivatives, and also we are discussing about their applications like in the Taylor's polynomial and in the Maclaurin's polynomial, and also we are using the first order approximation and quadratic, that means second order approximation. I hope all of you have successfully joined in the discussion. I would like to thank all of you for joining in this session. For today, this much from this session. Once again, thanks to all of you. So have you any question? କାହାର କିଛି ପଚାରିବାର ଅଛି କି?
ହ୍ୟାଲୋ ସାର୍।
ହ୍ୟାଲୋ।
ସାର୍ ଯୋଉ ଆପଣ ଟିକେ କହିପାରିବେ କି ଜିଏମ୍ ୟୁନିଭର୍ସିଟିରେ ଯୋଉ BSc ଜେନେରାଲ ଥିଲା ସାର୍ ଏଇଟା କୋଉଠି ଚେଞ୍ଜ ହେଇଛି?
ନା ନା ମୋର ଆଇଡ଼ିଆ କିଛି ନାହିଁ, ୱେବସାଇଟ୍ ଦେଖିକି ତମେ ଜାଣିପାରିବ ଭାବୁଛି।
ସାର୍ ରିଜନାଲ ସେଣ୍ଟରକୁ ତ ଇମେଲ କଲେ ବି ସେମାନେ ରିପ୍ଲାଏ ହିଁ ଦଉନାହାନ୍ତି।
ରିଜନାଲ
ଆଜ୍ଞା
ସେଣ୍ଟର
ସାର୍।
ତ ଭୁବନେଶ୍ୱର ରିଜନାଲ ସେଣ୍ଟର। ଆଚ୍ଛା ଏବେ ତୁମେ ଆମ ସେଣ୍ଟରକୁ ମାନେ ମେଲ୍ କଲେ କିଛି କଣ୍ଟାକ୍ଟ କଲେ କିଛି ରିପ୍ଲାଏ ଦେଉନାହାନ୍ତି କି?
ସାର୍ ଏଇଟା ମାନେ ରାଉରକେଲାର ନା
ନା ଏଇଟା
ସୁନ୍ଦରଗଡ଼ର?
ଏଇଟା ଗଭର୍ଣ୍ଣମେଣ୍ଟ କଲେଜ ସୁନ୍ଦରଗଡ଼ର। ୟା
ଶୁଣ
ଡିଷ୍ଟ୍ରିକ୍ଟ କଣ୍ଟାକ୍ଟ କରିକି ହଁ
ସାର୍
ଭାବୁଛି
ମୁଁ ଏବେ
କ୍ଲାରିଫିକେସନ୍ ମିଳିଯିବ।
ସାର୍ ମୁଁ ଏବେ ତ ସୁନ୍ଦରଗଡ଼ରେ ଅଛି, ଆପଣ ଯଦି ଆଭେଲେବଲ ଅଛନ୍ତି କଲେଜରେ ଏବେ?
ମୁଁ ତ କଲେଜରେ ଆଭେଲେବଲ୍ ଅଛି, କିନ୍ତୁ ମୁଁ ତ କଲେଜ ଏବେ ମୋର ଯେତେ ସେସନ୍ ସରିଯିବ ମୁଁ ବାହାରି ଯିବି। କିନ୍ତୁ
ହଁ
ଅଫିସ୍ ଖୋଲା ରହିଥିବ, ଅଫିସରେ ଆସିକି ଇନକ୍ୱାରି କରିପାରିବେ।
ସାର୍
ଠିକ୍ ଅଛି।
ଆପଣ, ହଉ ସାର୍ ଠିକ୍ ଅଛି।
ହଉ। ଆଉ କିଛି କ୍ୱେଶ୍ଚନ୍? Any question from any other? So we are going to end this session. Once again, thank you.